Today we are presenting our topic of project 2, which is timetable generation system. I am Nishant Kumar and I will be presenting the first part of the project. Here's how we have structured our presentation today. First, we will talk about the problem statement, then methodology, then and then our approaches, and then algorithms and implementation. Then we will show the results, the visualization, and its comparison analysis. Then we will conclude our presentation, and we'll talk little more bit more about our future work, and that's all. We are Nishant Kumar, Rishabh Anand, Nishant Kumar. Now let's start with understanding the timetable problem. The timetable generation problem is a very complex problem. We need to schedule classes for 100 of students across multiple departments while satisfying numerous constraints. These constraints are no students conflicts, like one student should not go into another subject at the same time. Same for the faculty conflicts, then no conflicts, like classes should be booked in two rooms. Classes between 8 p.m. and to 6 p.m. with lunch breaks, practical sessions in designated lab. Some has some different patterns like 1+1+1 lectures, like 1+2, etc. Our main objectives are to minimize uh, gaps between classes, minimize room switches, avoid early and late slots, balance faculty overload. We approach this as a constraint satisfaction problem. Our methodology involved data processing to create the necessary data structure, then implementing constraint checking functions, then developing three different algorithm approaches, which are constraint satisfaction with backtracking, genetic algorithm, simulated annealing. Then creating the visualization tool for results, analyzing and comparing algorithm performance. Our timetable is represented as a nested dictionary structure, which can be like timetable, day, then time slot, and then room. And then that will be the subject the day is specified. For example, here we can see that the day is Monday, the time is 8 a.m. to 9 a.m. The room is L204 and the subject is EE303. Let's talk about the input data structure. Like for the subject.csv, course details are like this. Like for subject, we have that the number of lecture, the theory classes, and the practical classes, and the lab location. For CS301, we will be taking 3 lectures, 1 theory classes, and 0 lab practical classes. Same for like CS402, we have 2 lectures and 3 labs. 3 practical classes, which will happen in lab CS lab 1. For rooms dot csv, for room capacity, it is like a room number, then capacity L101 has 120 students, CS lab 1 has 40 students. Dot csv has roll numbers and enroll subject. For example, a student with the roll number CS2001 has subject CS301, CS302, CS303, HS201, and MA201. So faculty.csv has teaching assignments like for employee ID S1, S2. Like for this faculty with the employee ID CSF001 has 2 subjects to teach, CS301, CS401, and this faculty CSF004 has only 1 subject, CS404. This structure allows efficient constant checking and manipulation. Now I will hand over to Nishant, who will explain the algorithms we implement in detail. So, right, go.
Thank you, Nishant. I am Nishant, and I'll be explaining the 3 algorithms that we have been implemented for the timetable generation. The first one is constraint satisfaction with backtracking. The second one is genetic algorithm, and the third one is simulated annealing. So each algorithm had different strengths and weaknesses for different scenarios suitable for different one. So let me walk you through with one on one different algorithms. So the first one is CSP with backtracking. So this algorithm sorts object by constraint level, tackling the most difficult ones first. Now the second thing is it tries to assign each subject to valid slots and rooms. The third one is if a conflict is detected, it backtracks and tries different assignments. And the fourth one is it continues until all the subjects are assigned or all possibilities are exhausted. The key advantage of CSP is it guarantees a solution if one exists. However, it can be large problem instances in case it will be exponential worst case complexity. So there are some key implementation functions of CSP. The first one is backtrack assignment. It is a co-recursive function that attempts to assign subjects and backtracks if there is a conflict. The second one is valid assignment. It checks if the current assignment violates any constraint or not. It also validates room, time, and instructor availability. The third one is generate lecture patterns. It prepares possible time room combination for each subject. It helps prioritize feasible operations before assignment. Now the second algorithm is genetic algorithm. So it inspired by the natural selection. So there are few points that has been in the genetic algorithm. The first one is we create a population of random timetables. The second one is we evaluate their fitness based on constraint violations and quality metrics. We selected the best timetables as parents, and after that, we create new timetables through crossover and mutations. These are the two important functionalities of genetic algorithm, and we have repeat these process for multiple generations until we get the best results. The genetic operators we have implemented has few things that has been included. The first one is tournament selection, which has size 3. The second one is crossover based subject based crossover, where child inherited each subject from each parent. And there are three types of mutations. The first one is time slot swap, which has 30% chance. The second is room change, which has also 30% chance. And the third one is day swap, which has 20% chance. Since the genetic algorithm does not guarantee an optimal solution, but it often finds good solutions and quickly scales to larger problems. So it is the best algorithm if we need to go for the large solution. Now, we move. There are some key implementation functions of genetic algorithm. The first one is crossover. What it does is it combines genetic material from parents to create offsprings. Here, genetic material is our subjects. It focuses on subject based crossover for timetable diversity. And the second function is mutate. It applies mutation operations, which is time swap, room change, and day swap. And it also applies variety and avoid premature convergence to get best results. The third one is evaluate fitness. The evaluate fitness measures how close a timetable is being conflict free. Fitness score is also based on constraint satisfaction and timetable quality. Now we move on to our third algorithm, which is simulated annealing. So simulated annealing, which starts with a random solution and gradually improves it while accept occasionally worse solution so that it can escape local optima. The key components of simulated annealing algorithm are the first one is cooling schedule, which controls how quickly the algorithm converges. And the second one is neighbor generator function, which makes small changes to the solution and creates a new neighbor generator and function, which is in case is the timetable. And the third one is acceptance probability, which decide when to accept the worst solutions. The key parameters that has been used here is the initial temperature, which is 100, and the second one is cooling rate. It is the rate at which the temperature decreases. So cooling rate is 0.98 we have fixed, and the initial temperature we have kept to be 100, and the iterations is 500. It is the number of attempts to optimize the solution. So we keep the iterations to be 500 because we need to check how optimized we can get. So it is the optimal number of iterations that we have picked by checking few number of iterations. So here is the simulated annealing implementations. So this is the main function of simulated annealing, which is generate timetable simulated annealing, which takes initial temperature, cooling rate, and number of iterations. So our solution start with, first of all, we create a random timetable using that create random timetable function, and the second function evaluate fitness is used to evaluate if the solution given by a simulated annealing is how good, and based on that it goes on each iterations and then find using get number function, it creates a neighbor by making a small change, and it evaluates the fitness of the solution. Then if neighbor is better than the current fitness which has been taken, then it accepts the solution, and if the neighbor is worse, then it accepts that solution or not based on the probability, and based on how much worse it is means and the current temperature differences. Then after that it will decrease the temperature according to the cooling rate, and in the last it will track the best solution so far, and it will returns the best solution at the end of that. So now I would like to call Rishabh, who will present our results and analysis.
Thank you, Nishant. I am Rishabh Anand. I will presenting our result visualization and analysis of the evaluated our algorithm based on execution time, quality metrics, and constraints satisfaction. Let's start with the performance comparison. CSP with backtracking took about 24.7 seconds. Genetic algorithm took about 7.5 seconds. Simulated annealing was the fastest at just 1.3 seconds. For solution quality, the genetic algorithm performed best with a source of 72.3, following by simulating simulated annealing at 70.1 and CSP at 68.5. All three algorithms successfully satisfy all hard constraints. Quality matrix. For individual quality matrix, we measure student gap between room switches for consecutive lecture, percentage of early and late class, faculty workload imbalanced. The genetic algorithm performed best overall with 12.4% early late classes and an average of 0.7 gap per student. Simulated annealing was close behind, while CSP produced acceptable but slightly slow quality solution. These are the visualized demo. We created several visualize to help analyze the result. Here our main timetable visualization showing the assignment across day and time. Each cell show the subject code of room. We also generate this additional chart. Room utilization percentage these are. And these are the subject distribution across days. And these time slot popularity. This visualization help administrator quickly understand the timetable structure and identify potential improvement. And these are our final timetable that we generate. Algorithm strength and the weakness. Base genetic algorithm. Good balance of quality and time. Explicitly optimize quality and matrix. It doesn't no guarantee of optimality. It not result vary between run. CSP guarantee solution if exists. Systematically explore search space. It doesn't slowest execution time. Does not optimize quality. Simulated annealing. These fastest execution good at escaping local optima, slightly slower quality than genetic algorithm. It doesn't sensitive to cooling parameters. Challenges and limitation. So we face challenges, complex lecture pattern handling, efficient conflict checking, balancing multiple objective and visualization issue, and our current limitation. So special case handling, limited department specific requirement, and dependency on the complete input and data. And these are conclusion. Successfully developed timetable generated that satisfied all hard constraints, optimized for student and faculty convenience, provide multiple algorithm option, include comprehensive visualization. These are key findings. Meta heuristic, genetic algorithm, and simulated annealing offer better scalability than CSP. Genetic algorithm provide best quality and reasonable speed. Simulated annealing provide fastest execution with good quality time. And this is our future work. Our constant s- satisfaction system has demonstrated significant potential, but several key development will enhance its capability and real world application. Future work will focus on two implementation phase, targeting performance optimization and advanced domain integration. Implementation work, we will boost system performance through parallelization techniques that reduce processing time by up to 8x for complex problem, and intuitive graphical interface will provide visualization tool and drag and drop functionality, making a system accessibility to non-technical users, and implementation tool. In future, advanced application will combine constraint satisfaction to optimize technique for large problem space. We will develop a specialized constraint library for healthcare, manufacturing, transport, and education system. And Nishant will show you the demo. Thank
Now let's see our code in action. Let's do the live demo. So we have structured our code in three different Python files. This is timetable generator, which is the main logic, and Nishant has explained us the implementation of all three algorithms. This file creates the visualization things, and this is the for the evaluation matrix we will use for the visualization. For the faculty, we have like 15 faculties for this live demo. We have 15 rooms and 55 students, which has each has five subjects enrolled, and the subjects are 25. Now let's run the code. We are using the main file, which takes combines the process and runs the all three file one by one. So main dot, it first generated a output folder which will have the files later on. Let's see the process. So generation of timetable using CSV took around 25 seconds for this small data set, and for our generation using genetic algorithm took around 7 seconds, and generating using took around 1.33 seconds. The process is complete. The CSV file is saved. Now let's look at the results. So this CSV file contains complete timetable generated by the simulated annealing algorithm. Each row represents a class with its day, time, room, and subject. We can see, for example, CS303, which is on Monday 9 to 10 a.m. in CS Lab 2, and ME402 is in L203 from 9 a.m. to 10 a.m. in Monday. Now, here is the visualization. This is the generated timetable. Each cell represents a class session with a subject code and room. The colors help us see the different subjects. Notice how the timetable is organized to avoid conflicts while optimizing for student convenience. We can see on that it generated from 8 a.m. some classes to there is a gap of 1 to 2 that slugs and like that, and this is how we have generated. This is the matrix comparison file, which is this, and then this is our room utilization chart. This shows that how effectively we are using available room. Notice that some of the specialized labs like these have higher utilization in general as compared to CS Lab 1, which makes sense given the limited number of practical sessions. This is for subject distribution, like how each day we are giving the classes. And this is the time popularity graph chart. That's all. Thank you so much. We are Nishant Kumar Rishavanand. Nishant Kumar. Thank you.